On January 25, 1999, an earthquake measuring 6.2 on the Richter scale tore through the coffee-growing region of Western Colombia. In the cities of Armenia and Pereira, concrete buildings pancaked, block walls sheared apart. Nearly 60% of all conventional structures in the affected area collapsed. 1,185 people died. When engineers arrived to assess the damage, they found something that stopped them cold. The bamboo houses were standing, not all of them, not perfectly, but in a zone where concrete had failed catastrophically. The structures built from Guadua angustifolia, the native bamboo species of Colombia's Andes, had absorbed the seismic energy and remained upright. The walls flexed, the joints rotated. The structures moved with the earthquake rather than against it. When the shaking stopped, the bamboo buildings were still there. The Colombian government commissioned research into what had happened and why. The engineers already knew the answer, but they needed data that would hold up in a building code. They got it. In 2010, Colombia published the NSR-10, its National Seismic Resistant Building Standard, and for the first time in the history of any national building code anywhere in the world, bamboo was written in as a recognized structural material with its own guidelines, its own load tables, and its own specifications. A grass had officially outperformed concrete in a real earthquake, and a government had responded by writing it into law. The United States has not. This is the story of a material that is stronger than steel by weight, faster to grow than any tree by decades, cheaper to build with than any conventional alternative, independently certified in laboratories across 3 continents, and written into the national building codes of Colombia, India, China, Ecuador, and Peru, but not the country that builds more homes per year than almost any other nation on Earth. And the reason it is not about structural engineering. To understand why bamboo belongs in this conversation, you need to understand what bamboo actually is. Because the material most Americans have encountered, like the chopstick, the cutting board, or the decorative screen in a hotel lobby, is almost nothing like the structural bamboo used in construction. Bamboo is a grass. That is the first disorienting fact. The largest species grow to over 100 feet tall, with stems up to 10 inches in diameter. Some species set a Guinness World Record for plant growth, nearly 4 feet of vertical height in a single day under optimal conditions. A bamboo grove that begins from planted rhizomes reaches construction-ready maturity in 3 to 7 years. An oak tree suitable for structural timber takes 60 to 150 years. A plantation of bamboo, once established, can be sustainably harvested every year for over 40 years. Cutting stimulates the regrowth. The roots stay intact. The grove regenerates. Raw bamboo culms, the individual poles, have a tensile strength of roughly 28,000 pounds per square inch, comparable to mild steel. But that comparison understates the case. Steel is heavy, and a structural bamboo element achieves its performance at a fraction of the weight, giving it a tensile strength-to-weight ratio 3 to 4 times that of steel. Materials engineers have given it a nickname: green steel. When bamboo is processed into engineered laminated products, the same concept as cross-laminated timber or engineered hardwood, independent laboratory tests have pushed tensile strengths beyond 400 megapascals into territory that competes directly with structural steel alloys. It is also, as Colombia discovered in January 1999, one of the most earthquake-resistant building materials that exists. The reason is mechanical. Bamboo's hollow cylindrical structure, with thicker walls at the base and a natural fiber alignment that runs the length of the culm, allows it to absorb and dissipate energy rather than resist it rigidly. Concrete resists force until it doesn't. Bamboo bends. In the language of structural engineering, it is ductile. In the language of a person standing inside a building during a magnitude 6.2 earthquake, it is the difference between walking out and not walking out. The man who did more than anyone to prove this to the world was born in Manizales, Colombia, in 1949, in the same Andean coffee region that the 1999 earthquake would later destroy. Simón Vélez is an architect. His father and grandfather were architects. He began working with bamboo in the late 1970s when he was searching for a way to build well in a country where most people could not afford the materials that architecture schools taught him to use. He developed a technique that solved the central engineering problem of bamboo construction, the joint. Raw bamboo culms are hollow. Standard mechanical fasteners, bolts, screws, plates, concentrate stress at a point and split the culm under load. Vélez's solution was to inject liquid cement into the bamboo at the connection points before installing the hardware. The cement filled the hollow section, distributed the stress over the full cross-section of the culm, and allowed standard structural steel plates and bolts to be used without failure. A simple innovation, a profound one. By the 1990s, Vélez had built structures across Colombia that could not be explained by the conventional understanding of what bamboo was capable of. Churches, bridges, multi-story residences, hotels. He combined guadua with concrete foundations, copper roofing, and terracotta tiles in buildings that were structurally sophisticated, architecturally striking, and built at a cost that made conventional construction look wasteful. In 2000, the Zero Emissions Research and Initiatives Foundation, ZERI, invited Vélez to design the centerpiece of their pavilion at Expo 2000 in Hanover, Germany. The result was a circular bamboo structure 130 feet in diameter and 55 feet tall, covering 2,000 square meters. Before construction began in Germany, engineers at the universities of Braunschweig and Stuttgart and the Science University of Bremen subjected the design to structural analysis. The building was assembled first in Colombia, then disassembled and rebuilt in Hanover. It received a full building permit from German authorities, the first bamboo structure ever to do so in Germany. Over the 5 months of Expo 2000, it received 6.4 million visitors. It was the most visited pavilion at the entire exhibition. After the 1999 Colombian earthquake, Vélez designed an emergency housing reconstruction program for the coffee region, funded by the Federation of Coffee Farmers. The ZERI Foundation calculated that on 100 square meters of land, a family could harvest enough bamboo each year to build a 2-story house with a large balcony for approximately $1,750 in materials, built mostly by the owner. The structural system was essentially the same as the ZERI Pavilion. The same material, which had been certified by European universities, displayed at a world exposition, and visited by 6 million people, was simultaneously being used to house earthquake survivors in the Andes for less money than a used car. Vélez has now completed over 300 buildings in 11 countries: Germany, France, India, China, Jamaica, Brazil, Mexico, Panama, Ecuador, Colombia, and the United States. Bamboo buildings do exist in America. They are just not built under normal building permits. Which brings us to the question this video is actually asking. Not whether bamboo works. That is settled. Not whether it has been engineered, certified, and proven in real seismic events on 3 continents. That is also settled. The question is why, when you go to a U.S. county building department with a set of stamped engineering drawings for a structural bamboo home, you will almost certainly be told no. The answer starts with 4 letters, IBC. The International Building Code is the model code adopted by most U.S. states and municipalities as the basis for what can and cannot be built. It recognizes wood. It recognizes steel and concrete and masonry. It recognizes engineered wood products like cross-laminated timber and laminated veneer lumber. It does not recognize bamboo as a structural material for residential construction. It is not listed. There are no design tables, no allowable stress values, no span charts. For the purposes of the American building permit system, structural bamboo does not officially exist. This is not because bamboo has not been tested. The International Organization for Standardization has published bamboo structural design standards since 2004. Colombia codified it in 2010. India, China, Ecuador, and Peru all have national bamboo building standards. The ISO framework is comprehensive and technically rigorous. The structural engineering is not in question. The pathway for getting a material accepted into the International Building Code, IBC, requires extensive ASTM testing, a standardized series of tests conducted to American Society for Testing and Materials Protocols, followed by evaluation by the ICC Evaluation Service, which produces reports that allow local jurisdictions to recognize a material as code compliant. That process takes years, it is costly, and it can require hundreds of thousands of dollars and a sponsor to fund it. Who funds ASTM testing? The industries that benefit from the results. The lumber industry, whose products are already in the building code, has no financial incentive to fund testing that would certify a competitor. Bamboo grows in 5 years. Timber takes 60 to 150 years. A bamboo plantation does not require the same capital-intensive land management, harvest equipment, mill infrastructure, or decades-long supply chain that the $237 billion US lumber and wood industry is built around. Bamboo, if it were code-compliant and widely adopted, would directly threaten the framing lumber business that provides the structural skeleton of almost every house built in America. There is one company that has navigated the certification pathway. Bamboo Living, based in Hawaii, holds ICC Evaluation Services Report, ESR 1636, which certifies their specific prefabricated bamboo pole system for use under the International Building Code. Their homes can be permitted, but the certification is proprietary, narrow, and expensive, and it applies only to their product, built their way, and installed by their team. A builder in Texas who wants to design a custom structural bamboo home using locally grown material and their own engineering drawings cannot use that report. They must apply jurisdiction by jurisdiction for an alternative materials and methods approval, a process that requires engineering submittals, peer review, local approval, and in many cases years of back and forth, even when the structural calculations are correct and the material has been proven in real earthquakes. Most jurisdictions deny the application before that process concludes. Here is what this means in practice. Colombia, which suffered a magnitude 6.2 earthquake in 1999 and watched bamboo stand while concrete fell, responded by writing bamboo into their national building code within 11 years. The United States, which has not had a comparable seismic event in its bamboo-compatible growing regions, has done nothing. A material that was independently certified by 3 German universities, received a building permit in Germany, hosted 6 million visitors at a world exposition, and was subsequently codified in 5 national building standards, cannot receive a residential building permit in the overwhelming majority of American counties. The structural case for bamboo is not where the battle is being fought. The battle is in the code development process, where the organizations that benefit from the current material monopoly have every financial incentive to ensure that the testing required for bamboo recognition is never funded, never conducted, and never completed. Now, the honest part. Bamboo construction has real limitations that anyone considering it needs to understand. Raw, untreated bamboo is susceptible to insect infestation and fungal decay, particularly in humid climates. Treatment methods, including borax solutions, heat curing, and traditional smoking, address this substantially, but the treated material requires different handling than lumber and different specification than a conventional building permit assumes. Engineered bamboo products, like cross-laminated bamboo panels, solve most of the durability issues, but they currently must be imported, primarily from China and Southeast Asia, which affects both cost and the carbon footprint for American builders. The strength claims also require precision. When you hear that bamboo is stronger than steel, the accurate version is that bamboo has a higher tensile strength per unit of weight than mild steel. In absolute terms, high-yield structural steel outperforms bamboo. The strength-to-weight comparison matters enormously in construction. A lighter structural element is cheaper to handle, cheaper to transport, and imposes lower loads on foundations. But it is not the same as claiming bamboo beats steel in every metric. Any builder specifying bamboo structures needs engineers who understand those distinctions. Within those constraints, the material does what the earthquake proved and what Simón Vélez's 300 buildings confirm. It carries loads. It resists seismic forces. It grows back. And a 2-story house can be built from it for a fraction of what the lumber industry charges for the same structure in dimensional pine. The Colombian coffee farmer who rebuilt his home after the earthquake that killed 1,100 of his neighbors did not do it with an approved submittal and an ICC evaluation report. He did it because bamboo grew on his land, and he knew how to build with it. And when the earthquake came, it was the only thing left standing. In the United States, you would need a lawyer to do the same thing. That gap between what a material can do and what a building code will allow is not an accident. It is a business model. And the people paying for it are every homeowner who has ever been forced to frame a house in timber when the grass that could replace it grows 36 inches in a single day and reaches structural maturity before the tree it replaces has grown its first decade of rings.